Okay, so from your velocity time graph, you calculated the slope. What was that slope? How did you do that? Okay, so in general, your slope is going to be a rise over run, right? And in this case, it was delta V over delta T, right? That's a change in velocity right? Change in velocity over a change in time, right? That's how it always works. When you're doing a slope and you have a rise over run, it's the change in whatever's happening in the y-axis divided by the change in what's happening in the x-axis. So in this case, it was a change in velocity over the change in time. And it's possible as you were doing that, you were starting to think about things that you've seen before in the class, I hope. And then, what were the units? Yeah, because delta V was going to be meters per second. Delta T was going to be seconds. And then we just have to remember how to do like algebra math, right? So it's meters per second divided by, right? You can write that as seconds over 1. And now we have 2 fractions divided by, right? So you say, you take the first one and you multiply by the reciprocal, right? And so that's how you get meters per second squared. Yeah, Kyler.
Oh, you want to use this on the test Friday or no?
Your notes? Yes.
Yay.
Your test is not Friday. Your test is next Friday.
Yeah. Well, today.
Yeah, like your test isn't tomorrow. Your test is a week from tomorrow. Okay? Good job.
Yeah.
All right. So guys, what is the slope? What is it?
M squared. Meters over second squared.
A bigger statement.
That's right.
Meters per second squared is the unit. What, Brooke? No, sorry. Yes, Brooke. My God. It is acceleration. Oh my goodness. Acceleration. That's what that is. Whee! Delta V over delta T. You guys, that's huge. It's so exciting. Okay, so we're going to just summarize that real quick. The big idea was that the slope of the position time graph. Think about that. Position is x. Time is t, right? So the slope is delta x over delta t. And what was that? No? Velocity. Oh, right? And the slope of the velocity time graph was, now you can say it, Ian, acceleration. So, the slope of a position time graph is velocity. The slope of the velocity time graph is acceleration. Think about what slope means and see if that makes sense. Can anybody reason through that? Why the slope of the position time graph is velocity and the slope of a velocity time graph is acceleration? Hayden, what do you think?
Because with position and time, you're actually doing the moving, and then with velocity over time, you're saying how much or how much more or how much less velocity is going over time.
Awesome. Okay. So it's about, right, slopes are about change, right? And so this means how fast the position is changing. And acceleration is how fast what is changing? Velocity. And remember that you're thinking about sort of what does it look like on your speedometer, right? If you think about what your speedometer looks like, you're at a certain velocity, and if you see that needle moving really fast, that means it's a big acceleration because your velocity is changing quickly. So you could imagine that graph of velocity versus time would be quite steep because for each little chunk of time, it's going to have a big change in velocity. All right, how are you doing? Tell me if you're with me. Okay? All right. Good, good. Oh, that's the end of that page. All right, so let's look again. What are we looking at? Oh my goodness. What are we looking at? Tell me. Okay, so this was like data from the cart, right? Constant velocity. So describe the x versus t graph to me. What?
The position is moving forward.
Okay, but like if you just look at the graph, describe it in words. It's a slanted line. Cool. What about the velocity versus time graph?
Straight kind of going down.
What do you think, Gwen? It's straighter, almost flat. And what kind of slope is that? 0. Okay.
It was kind of.
What's that?
It looks like it's deeper.
It is a tiny bit, but you know, we're trying to go for that sort of ideal situation here. So when I look at this, I'm going to use a different color because I'm just so fancy. Okay. When we calculate the slope of this line, right? That's our rise over run, right? That's our delta x over delta t. Yeah? How about this? How do I calculate the slope here? The slope is 0, right? Because there's no rise. So if this delta x over delta t gives you this number, right? This is the slope. This slope gives you that. Right? So we go like this to that. So it's x, v, a. Does that make sense what just happened here? What's that? Yeah, and you can't, you want to know something fun? Do you want to know what the slope of the acceleration versus time graph is? Does anybody know? This is a fun fact to use at cocktail parties. Not that you go to cocktail parties. It is called jerk. Yes. Why does it make sense?
It's like.
Yes, exactly, exactly. What we're going to figure out next, can you, thanks. Next unit, we're going to actually figure out what causes acceleration, and the answer is force. And so a change in acceleration is going to be caused by a changing force. So that would be jerk. All right, sweet. Okay. So I'll just write a couple things that I said. So when v is constant, this means that acceleration is 0. This is a really, really important thing. Put underlines, put it in a box, okay? Because at some point we're going to do other problems where we talk about, we're describing something and it says that the velocity is constant. And you need to be able to go immediately from a statement of velocity is constant to acceleration is 0. That needs to be like implanted in your brain, okay? So when velocity is constant, the acceleration is 0. And hopefully that makes sense because acceleration is delta v over delta t, and so there's no change, right? That's what constant means, okay? It might seem like I'm saying a lot of the same things over, and I am, but it's just because trying to get at it a couple different ways. And one of these things is like, sometimes someone will get it the first time I say it, but then someone needs the 5th time. So, all right, how do you feel about this? Good? All right, we're hopping through this. Aha, I'm gonna pause here and go take some data. So what we saw with the cart going down a ramp was that the acceleration is constant. And then the slope of the v versus t, right, delta v over delta t, the slope was, right, that acceleration. If you calculate this slope, you will get this number. Okay, that's how it goes. And then the slopes here kept increasing. Let me write that over here. The slope kept increasing, right? And that slope, which is delta x over delta t, is the velocity. So that all should like come together in your head, right? Cool. Let's look. Oh, look, I gave myself lots of space down here to write, but that's okay. All right. I took data from those graphs that are in the notes, okay? And here's the data. I took them. What's delta t here? Do you guys see what I did? I took some data, and I have the time, the position, the velocity, and the acceleration, okay? So I want to analyze delta things over delta t's, right? Because that's the interesting thing here, okay? So what's my delta t here? I actually have it the same for all of them. Who's good with quick math? 0.2. So these are all 0.2 seconds, right? Okay. I want you to take a moment and actually figure out the other ones. Now I'm going to record. All right, so those are our delta x's. Can you make an observation? So just remembering, we're looking at the same delta t's this whole time. August.
They go up.
They go up. So delta x keeps getting bigger. What do you think that means in sort of other language? How could you describe that? That the delta x, which is displacement, keeps getting bigger. What's that?
Increasing.
It's increasing, okay. How else could we phrase that? What do you think, August?
It's accelerating.
It's accelerating in your sort of normal everyday life. You feel like this is accelerating. Accelerating, so why do you think it's accelerating?
Because the distance it's traveling between the turtles keeps going up.
Yes. Okay, Jimmy, is that what you're going to say? The distance, right? Sorry, I'm going to try that again. It travels further each second. Okay, and it's true that we're just looking at these time intervals of 0.2 seconds, but each second it's covering more and more distance. Does that make sense? Okay. And what about our delta V's? What were those?
More or less going up by 0.2.
Yeah, they were all about, it was like 0.21, 0.2, 0.22, 0.2, right? So delta V staying equal, right? It's about the same. So same, oopsies. That means the same change in velocity each second. Oh my goodness, my handwriting leaves something to be desired. Sorry about that. And then what are your observations about acceleration? What are those numbers like? 1.04, 1.08, 1.08, 1.04. It goes up and then down. But in terms of like looking at that as a number, they're pretty darn close, right? So A is pretty constant. Yeah? Okay. Does that make sense? How are you feeling? I get one thumbs up. I get a couple glazed over looks. Okay. Just kidding, there's more. All right, I want you to look at a motion graph. So what I did is I took that data, and I don't know if you noticed it was color-coded, and I drew it like on a meter stick. Do you remember when I did this for the constant velocity situation? Right? And here, right, that was our delta x. And our delta x's for constant velocity all looked pretty similar. Yeah? But now, check them out. That's our delta x. And so, can you make a statement about this? This is for our acceleration. Can anybody make a statement looking at that?
Acceleration is growing.
Say that again.
Acceleration is growing.
From this motion graph, you cannot say the acceleration is growing. We actually took this data from a situation where acceleration was constant, so it wouldn't be growing. But what is growing? Brooke?
Velocity.
How can you tell velocity is growing?
Because I don't know.
You're not wrong, but it's good to actually know why you know that. Yeah, Jimmy. There's more change in where the points are. So the distance between each point is growing. So that means that the average velocity in here is less than the average velocity here. Right? So if you look at each of those sort of sections, look at this section. For it to go from that green to that blue, it had to be going reasonably fast, right? Versus going from that red to the orange. It wasn't going as fast. So that, Brooke, is why you know that it's going faster. It's because it's traveling the same distance in the same time, okay? And the trick with these motion graphs is that each dot is the same amount of time away from each other, okay? Okay. Questions on this? Does this seem clear? We actually have a good amount of time. So there's just one last little thing, and then we're actually going to have some time to do that interactive. Okay? So the last thing, cool. Wait, hold on. Is this. Because your test is coming up, this is good to bring back. Who remembers what we were talking about with velocity and acceleration, and if they were in the same direction or not same direction?
Plus sign.
Yeah, you see the plus signs and the minus signs? Remember we did like a moving man set? So if the velocity and acceleration are in positive direction, both, then it's speeding up, okay? What do you think about number 2? Which way is it actually moving? Positive, okay? And we say that right is positive. And so if the acceleration is negative, what does that mean? It means it's slowing down because delta V is negative. Does that make sense? Delta V is V final minus V initial. You've done some problems like this, right, where we talked about that. But what does this actually look like? It looks like that. Ooh. Right? If that's your V and T, it's a negative slope. Take a second and let that get in your brain. Does that make sense a little bit? Okay, so the actual change in velocity is negative. And that's what a negative slope means, right? Okay, when you actually do the thing moving to the left, right, because the velocity is to the left, and then the acceleration is positive or negative, we're not going to go through all of those, but you can convince yourself that if they're in opposite, if the velocity and acceleration are in opposite directions, it's slowing down, and if it's the same, then it's speeding up. And then in the notes, I just threw in this thing from last time. Okay?